Is Parthiv Haldar here? Sorry.
Hi.
No, sorry, Akhil Sivakumar. Sorry.
Yeah,
Akhil Sivakumar.
Can you hear me?
Yeah. Yes, we can hear you. You may share your screen.
Okay.
And I will stop you at 13 minutes. So in the next 2 minutes.
Okay.
Try to
so you see my screen?
Yeah.
Okay.
Yes.
So
now our last speaker of this session is Akhil Sivakumar. I think I missed him. So he will be talking about the fluctuating hydrodynamics via holography. Yeah,
okay.
Akhil, please.
Hi, I begin by thanking all the organizers of ISM for giving this opportunity to speak, and in general for organizing such a nice week of seminars. So I'll be talking about fluctuating hydrodynamics via holography, which is a general perspective on the kind of projects we have been doing in our last 2 years, which is to look at general real-time ADS-CFT calculations in a particular way. I'll be mostly talking about this work here and a bit about this work. And this work is also like an ongoing thing, which is on the same set of concepts. And then this is my extended list of collaborators. So let me start by motivating the problem. So we know the fluid gravity correspondence maps long wavelength deformations of dual black waves to long distance excitations or hydrodynamics of holographic plasmas. The original fluid gravity program analyzes Gaussian normal excitations of black waves. They find there are long-lived Gaussian normal excitations, and then you rewrite the boundary stress tensor in a fluid appropriate way, and the conservation of the boundary stress tensor then gives equation motion for the boundary fluid. To summarize, over large distances, the plasma behaves like a dissipative fluid governed by a Navier-Stokes equation. Then but we know that a dissipative fluid description is only an approximation to the more complete picture of fluctuating hydrodynamics. So the reason is that the microscopic modes which cause dissipation also affect the hydro description as some stochastic forces. So this should be thought of as a fluctuation dissipation relation. And in addition, there are statistical fluctuations of the hydrodynamic modes themselves, which are long-lived. And then, as you realize that once you start accounting for these long-lived long-lived fluctuations, it kind of makes your hydrodynamic theory sick. And you can check this reference for some discussion of this. So to understand this paradigm a bit, we could consider a simple toy model, which is like probing a fluid with a particle, say considering a pollen moving in air or something. So at low energies, we see only hydrodynamic modes. The presence of microscopic modes like molecules themselves is diagnosed from the Brownian trajectories of the particle. The lesson is that the low energy description is an open FT field theory of the hydrodynamic modes and probes interacting with microscopic modes, say molecules. In other words, the fluid has fast relaxing or Markovian modes. That's my definition of Markovian for the context of this talk. And long-lived or non-Markovian modes. We may integrate out the fast modes while retaining only the slow modes of the fluid to get a Wilsonian open EFT. And you can refer to Loga's talk on Tuesday for a detailed, more elaborate motivation of this. So having motivated the Wilsonian EFT perspective for fluctuating hydrodynamics, there are two technical questions to answer. First is that given a model, how do we indeed separate out slow modes from fast modes and selectively distill them out? And this talk is mostly about that. I'll motivate a formalism which does this, at least for holographic systems. And then the second question is, how do we incorporate the effect of statistical fluctuations? So from the field theory side, you would say we have to study the field theory as a Schwinger-Keldysh path integral, where you track the evolution of the whole general density matrices, or mixed states rather than pure states. And in holographic models, we know that boundary statistical fluctuations are dual to Hawking radiated modes from the black plane. So what we do is we use a novel Schwinger-Keldysh version of black plane geometries. So for those who know what a Schwinger-Keldysh path integrals, it's a double path integral and so on, which you kind of mimic by using a glued double black plane solution and so on. I might not be able to go into the details of this construction because of time constraints, but hopefully we will. But this is the short summary of how to deal with the second question. So this is the outline for the talk. So I'll talk about distilling out the fluidic modes. Then I'll give an example of the final goal, like how to understand this paradigm of Wilsonian EFT by considering the example of deriving a nonlinear Langevin equation for a Brownian particle in the holographic plasma, which considering a dual string moving in the bulk and so on. And then if time permits, we will talk about Schwinger-Delitzsch black brains. And then we will summarize and then float some future directions. So, like I said, we need a general prescription to separate out Markovian and non-Markovian dynamics. Focusing on a d-dimensional CFT, a working principle seems to be to implement an SO_d-2 harmonic decomposition of the excitations. So, this is plausible from the bulk. As for generic manifolds of time M2 times S_d-1, where the 2 and d-1 denote their dimensions and S is some maximally symmetric space, this separates out Einstein and Maxwell perturbations into gauge invariant sectors. Why Einstein and Maxwell? Because we are interested in the long distance regime, and the players there are all the conserved quantities like energy and charges and so on. So we are motivating a setup where like hydrodynamics modes are labeled by the wave vector K and the representation of transverse SO_d-2 rotations to this K. So this is similar to the way we think of particles as labeled by their little group representations and so on. So there are like this is some notation setting up, like these are tensors and vectors and scalars of this such a harmonic decomposition, and there are so many of these guys. So our proposal is that each of these excitations of the hydrodynamic theory dualizes to a bulk scalar, which is, so to speak, a master variable in the bulk, which captures the dynamics of bulk fields, the Einstein-Maxwell fields in the bulk. So more explicitly, the bulk solutions for Einstein-Maxwell fields can be written like this, where you see these phi d minus d, phi 3 minus d, and so on are the master scalars I mentioned, and they capture the bound. They do a harmonic decomposition of the sources, and then of the dual boundary currents and so on. To see this, like if you have a U1 current in the boundary, the spatial current can be decomposed by this SO_d-2 into some vector and scalar. And then you see that since the vectors are transverse, they are trivially conserved. And in some sense, they should be, that kind of indicates there should be short-lived modes because there's nothing non-trivial going on there. And indeed, you find that only JS leads to non-trivial dynamics, and it shows charge diffusion and so on. Similarly, for the stress tensor, you can decompose the tensor, the stress in the SO_d-2 fashion, and then the tensor part here is trivially conserved and doesn't lead to any non-trivial or long-distance dynamics. It's a short-distance mode, and the TV and TS denote transverse momentum diffusion and pressure waves respectively. And the cute fact about at least these four sectors explicitly written here, if you notice, I have like kind of like suppress the details on the scalar sector of the gravitons, is that all these scalars come from satisfy equation motions which extremize a simple one parameter action like this, which is a dilaton deformed Klein-Gordon action with a simple index M, which we call the Markovian index for obvious reasons. And then these M's can be mapped to each of these sectors I have explicitly written by this identification. And the thing about the scalar sector is that the action is slightly more complicated, but it is almost along the same thing. So the thing you have to notice here is that for these things, these sectors which I advertise as short scale sectors, short-lived sectors, the scalar directly maps to the gauge field in the bulk. But for these long-lived sectors, it is actually the radial momentum of the scalar which maps to the gauge fields in the bulk. So the fact about this general class of scalars, their equation of motion and their solutions and so on, is that when you compare the boundary radial momentum, 𝝅m always have derivative. 𝝅m's always have derivative expansion in terms of the boundary value of the field itself. So based on this like a difference on what is the bulk gauge field, whether it is 𝝅m or 𝝅m, this is interpreted as a local expansion for the sourced Markovian fields and the equation of motion for the non-Markovian fields. So the boundary condition for the Wilsonian EFT is to fix boundary sources for m+1 greater than 0, which are the Markovian modes, which directly map to the gauge fields, and 1-point functions for the m+1 less than 0 modes, which were the non-Markovian fields. Which this is like explained more by Loga in his talk. So this is a table summarizing these boundary conditions. For the Markovian sector, the usual so this first column is a Markovian sector, second column is a non-Markovian sector. The usual GKPW boundary conditions, which tells you how to calculate correlation generative functionals, will tell you in the Markovian sector you have to fix phi m, and in the non-Markovian sector you have to fix pi m. But in the Wilsonian boundary conditions motivated here says you go to this field basis of dual effective dual scalars, and then you fix the phi m, like you put Dirichlet boundary conditions for both all scalars. So like I've like talked about decomposing these scalars, writing FT theories, like suggested Stringer-Keldysh path integrals and so on. But how do you indeed make sense out of this, right? A simple way to make sense of a Wilsonian EFT is by mapping it to a stochastic differential equation. There's a general procedure to do it, as done by these guys. So as a simple example, consider the particle probing the plasma, the Brownian particle. The bulk is dual. In the bulk, the particle dualizes to a string which starts from the boundary from the particle, but then goes all the way to the black brane and dips into the horizon and so on. A nonlinear Langevin equation for the Brownian particle can be derived from the bulk dynamics of the Brownian string, which looks like this. So you notice that in addition to the usual dissipation and the stochastic force, you have a usual drag and stochastic force. There's a part of the drag which is stochastic itself, right? And it comes with a coefficient zeta gamma, and the stochasticity is captured by the same noise variable. And in addition to the noise, in addition to a simple Gaussian nature of the noise variable, so it's no longer Gaussian. It has non-Gaussianities captured by some parameters like this. There's some mainly the zeta n, which is a non-Gaussianity parameter, and then as in the familiar case, there's a fluctuation, the usual fluctuation dissipation relation, which relates f square, which is the variance of the noisy force with the drag. Now there are additional nonlinear fluctuation dissipation relation, which relates the non-Gaussianity in the probability distribution to the nonlinearity in the dissipation. Right. So how do you go about doing this in the bulk? Like, so how do you capture these nonlinear corrections? As general, you have to, like, more than the linearized equation motion for the string, you have to like add in interactions, like nonlinear corrections in the bulk. And then this noisy part really comes from doing a careful analysis of the Hawking radiated modes of the string. And it's crucial to include them correctly, and it's crucial to include them correctly at the horizon and so on. And that's the crux of like all this calculations, that you have to carefully account for Hawking radiation to see the effects of fluctuations in a consistent way. And the signature of the consistency is these fluctuation dissipation relations, which have been indeed like derived independently from the field theory side, like in this work. Like by assuming some weakly coupled path and all. But the point here is that you naively impose, you go ahead and like accommodate Hawking radiation effects in using our techniques, and the bulk calculation directly gives you these and which are consistent. How much time do I have left?
You have 2 more minutes left.
Okay, so maybe I'll like quickly go through Stringer-Keldysh path integrals. So open systems are described by reduced density matrices. The natural generative functional, once you consider density matrices, so general mixed states, are like general correlators like this, where you can general correlators where you can like act with operators on either side of the density matrix. And the path integral realization of such a calculation would need you to really act with operators separately on the left and right side of the density matrix. And then the appropriate path integral is defined on a closed time contour, okay, where the upper and lower legs on this time contour really denote the left and ket and the bra evolving forward, and you kind of think of the bra as evolving backward, and then they are identified at some future time point, indicating this tracing. And this is like a cartoon for creating some initial thermal density matrix by evolving with some beta time and so on, which is more familiar. And so there's a bulk realization of this. So the point is now that how do we like go about doing such a calculation in the bulk, and why is any of these calculations new or only possible at this point, right? So the point is that like you have to realize these bulk calculation, especially CFT path integrals of this kind, string-equal CFT path integrals from the bulk, and which involves understanding the gravitational saddle which really captures this path integral. And such a workable prescription, I should say. Like there have been attempts at deriving such an object before, and this is a workable prescription for doing these calculations, where they think of this black hole as a complexification of a usual short shell black hole, where you consider the black hole at a single in the ingoing Finkelstein time, which is crucial. And then you consider a single time slice of the black brain in ingoing Finkelstein time, and then you say like the fixed time radial coordinate has this analyticity. So whatever excitations you trigger on this, black brain should have this analyticity condition. That is that at a fixed time, if you consider a radial contour, the solution should be analytic on a contour like this. So you'll notice that like there are two asymptotics now, which is good because we wanted a path integral where there are two CFTs, one for the Ket evolution and one for the Bra evolution. And the idea is that you end up getting some black hole saddle like this, this is some exterior region, two copies of it glued along some horizon, say this shaded region. And then in the far past, you probably have this is a cartoon picture, like this not, but still like you have a past thermal circle in the boundary and a Euclidean black hole in the bulk and so on. So, but I should maybe add that like this is a prescription, and it seems to give you consistent answers even when you really do calculations with Witten diagrams and so on, like say contact interaction Witten diagrams and so on. So let me summarize. I motivated a formalism to distill out fluid modes of different hydrodynamic natures and introduced alternate boundary conditions appropriate for the Wilsonian FT field theory. So these are the future directions. Like one would like to understand these calculations as you consider bulk exchanges in Witten diagrams and even bulk loops and so on, and which is crucial to understand the phenomenon of long-time tails in hydrodynamics, which is the fact that correlation functions don't really decay as you expect. This is part of the sickness I mentioned in the motivation. So then you might want to go further and derive the saddle, because as I said, it's a prescription. You might want to understand why is the structure of black hole geometries true, as in like you continue think of them as analytically continued in radial coordinate or something, and then it seems to give you the right Shingle-Keldysh coordinates. And you might want to even go further and describe such a saddle away from equilibrium, like because at this moment you're thinking of a black brane, the ordinary short shell black brane, but then perturbatively excited. But you might want to derive a Shingle-Keldysh saddle for like configurations really away from equilibrium, corresponding to away from equilibrium boundary plasmas and so on. That's it. I thank you all for your attention.
Okay, thank you very much, Akhil, Sivakumar, for your nice presentation. If there is some short questions we can pick up, we are already late because the next session starts at 2.
Okay, I had a small question.
Sure. Yeah.
Yeah. So actually, yeah. So this the scalar. I mean, this decomposition you introduced into Markovian, non-Markovian. Maybe I miss it. I mean, is it related to how these modes couple to gravity in the bulk somehow? That I mean, what is this classification?
The classification simply from the hydrodynamics, right? It's just the fact that if you can decompose a current in this way, like here, and then if you can calculate the correlators of the current, the Markovian guys have short scale correlations, and the non-Markovian guys have long scale correlations. And then when like in usual case, when you derive the EFT, you don't want to integrate out the stuff which has long scale correlations, only the stuff with short scale.
So my question was about the action you have written down actually. So there's this coupling through this kappa. So is a statement that somehow the M depending on how it how the coupling becomes stronger. It's weakly coupled in the bulk, then it is one class of modes. It's the hydrodynamic mode.
Yeah.
So that's the classification, right? So is that
So it okay. So just looking at the effective scalar action for these bulk scalar modes, it seems like you're modifying a Klein-Gordon scalar by amplifying either its bulk dynamics towards the boundary or either towards the horizon.
Exactly. Is that the class? Is that the distinction between the two?
So from the perspective of just the equation of motion, that seems to be the distinction. Yes.
Okay. Thank you.
And but it's non-trivial that like at least these 4 sectors you can have a uniform like a simple one parameter classification of these modes. Yeah.
So this dilaton kappa basically tells you that.
Yes, right. Yeah.
Okay. Thank you.
Yeah. Thanks for the question.
Okay. Yeah. If there are no other questions, let us thank Akhil for a nice presentation.
Yeah. Thank you.
Over to the host.
All right. Thanks, Kamal. Thanks to all the speakers. So, like always in this conference, let us reconvene at 2:15, 2:15, 𝗬𝗫 2:15. Thanks, everybody. And again, we'll be using a different post-lunch Zoom link to do so. See you then. Bye-bye. Thanks. So team, we can end the recordings and close the meeting.